Hello, we are the Aerodynamic Capabilities and Analysis of Forward and Backward Swept Wings group. I'm Liam McNeil. With me is Megan Albright, Anne-Marie Bernardi, Ryan Holtman, and Alex Rendino. The team is as follows. Megan Albright was the team leader for this semester's project. She was also in charge of the structure of the actual wing. Anne-Marie Bernardi, she was in charge of the aerodynamic calculations for this group. Ryan Holdman was in charge of the accounting and the balance. I was in charge of the safety and making sure that our risk plan was followed. And Alex Rendino was in charge of the overall manufacturing of the wing.
For this project, the question we wanted to answer was, do forward swept wings perform better than traditionally used backward swept wings? Some background information that is important to know for this experiment is that aircraft traditionally use backward swept wings. Forward swept wings could possibly provide a higher lift-to-drag ratio, and should the forward swept wing be more aerodynamic, it could lead to several environmental, societal, and economic benefits, such as better fuel efficiency in planes, better cost efficiency, and be better for both military and civilian use. The relevant variables, controls, and parameters for this experiment were lift, drag, angle of attack, airspeed, and pitching moment.
We will now be moving on to the methods used in this experiment. For the experimental conditions we tested, we had forward and backward swept wings with a control of a horizontal sweep. The wind speeds tested at were 60, 70, and 80 miles an hour, with angles of attack at 8, 0, and negative 8 degrees, respectively. On this slide, we have the design of experiment tables. Here we lay out our expected values for lift and drag and pitch moments based off of calculations. These values are generated for various velocities and angles of attack as shown. The test equipment that we used for this experiment was the backward and forward swept wings that we built, the wind tunnel, the force balance, which was calibrated using weights, and the lift and drag outputs, and the desktop software used to analyze the data from the force balance. The measurement techniques used were the use of a force balance, which was set up in the wind tunnel. This was calibrated using weights and the data was extrapolated using a program that read the voltages produced from the force balance.
For our procedure, we use 10 steps, and you can see them in front of you on the slide. Step 6, we repeated step 5, which is calculating the lift, drag, and pitching moment based on the parameters at 60, 70, and 80 miles an hour. Step 7, we repeated steps 4 through 6 for angles of attack of 8 degrees and -8 degrees, when initially we did an attack angle of 0 degrees. And step 8, we repeated steps 2 through 7, again with the forward and backward swept wings. Our schedule had many setbacks as different designs for the testing plan came from different inputs. One of these factors was that we planned on picking up the work done by Dr. Merritt initially and then had to redesign our experiment. Our schedule ended up being as shown. For our experiment, there were several different items that needed to be purchased. We needed one foam board to construct the actual wing out of, 3 rolls of ultra coat, which is the coating that goes over the foam wing and is then heat shrunk, 1 piece of aluminum stock to attach the fastener to, and 3 packages of fasteners. All these items came out to a total of $118. This slide has our risk assessment. Overall, we decided that our experiment had a low test risk. The biggest things for this experiment were making sure that we wore hearing protection when operating the wind tunnel, and also ensuring that our fastener that we built did not allow the test subject to fly out of the wind tunnel during testing, which we ensured did not by starting off at low speeds and then moving up higher and higher and making sure that the wobbling was under control.
Now we will start moving into the results of our analysis. Below are the results that we obtained for a horizontal wing. You can see that there's 2 lift and drags. The first one is measured in millivolts, which is directly into the data processing software. And the second one is in newtons, and that's after we did our conversion using our calibration. On this slide, you can see our results for our forward swept wings. Once again, there are 2 values for lift and drag, and these are obtained the same way as the slide prior. On this slide are our results for our backward swept wings. Once again, we do have 2 values for lift and drag. They are obtained and derived the same way as the 2 previous slides. Below are our plots for lift and drag of each of our wings at their different angles of attack. At first glance, it does appear as though forward swept wings underperform in lift, although it does seem that we have an outlier in the -8 angle of attack, as forward swept wings tend to perform better on lift. We do believe that this could be an outlier or a problem with our calculation or our setup. However, looking down at the drag, at all angles of attack, it does seem as though forward swept wings produce a lot of drag compared to the other types of wings, and this leads us to believe that they might not be superior. On this slide, we have our table of our lift to drag ratio for each wing sweep. On horizontal and forward swept wings, we do believe we have two outliers and that they are 19 and 44 respectively. We believe these to be outliers because there are no other values that are this high, and they also do not make any sense when using engineering judgment, and we will keep that in mind moving forward with our results. We will now move into the conclusion of our analysis. Based on the data collected, the group determined that the backward swept wing placement had the best aerodynamic characteristics. The image on image 7 is supposed to be backward swept, but moving forward, we will discuss our final determinations and conclusions. In the future, if this experiment was replicated, the team would leave more time for testing to be completed. This would also allow us to use the pressure taps and tubing that we had originally planned in order to receive a different data trend. The group would also remake their model with a 3D printed model to avoid excess areas of drag from freehand cutting and sanding the model. Although there were several sources of error, this lab allowed for the aerodynamics of horizontal, forward, and backward swept wings to be analyzed. Finally, we would like to acknowledge Dr. C.G. Merritt and Dr. C.D. Hoover for their help completing this project.